So in this topic, we're going to be talking about lumped capacitance. And so the reason for that, oh, yes, no question. Okay. Um, oh, and actually, I should mention, I have the chat like up on my other computer screen, so I should be able to see it if anybody has a question, but if I just seem to ignore it, then just feel free to speak up. Okay. Um, so in this topic, we're going to focus on transient or unsteady problems. And so just to remind you, both of these things mean that we have a dependence on time. Um, and for these types of problems, so time-dependent problems, we want to predict the temperature variation of a solid as a function of time, of course. All right, and so we are only going to consider cases in this particular unit in which the solid can be assumed to have a uniform or a lumped temperature. So in other words, the temperature that is spatially uniform throughout the entire transient process. So at any point in time during this heat transfer process, we're going to assume that the entirety of the body that we're studying has the same temperature everywhere spatially throughout. Okay, so we're going to do this by using what is known as the lumped capacitance method. This is simple and common. And so these types of problems are one in which a solid experiences a sudden change in its thermal environment. So a good example to kind of illustrate how we would use this process is the following, and we're going to use this example to essentially develop the entire kind of workflow of using lumped capacitance and to derive the equations that are going to be useful for you. Okay, so we are going to consider that we have a small hot brass ball of diameter 2 centimeters that is initially at a uniform temperature of 150 degrees C, and then it is quenched by immersing it in a large bath of fluid of lower temperature. So our fluid in this bath is 50 degrees C. We want to determine the temperature of the ball after 1 minute, so after some specified amount of time, if it's quenched in water or if it's quenched in air. And you'll notice that we have H values here. This, just to remind you, since I know it's easy to mix these up, this is not enthalpy. This is the convective heat transfer coefficient. All right, so essentially what we have is that we have some initial configuration where we have our large fluid bath here. And it is at a temperature T infinity. And then above the bath, we have this sphere of brass with a diameter D. And this is at, so this is at a temperature Ti initially. All right, and then we are going to plunge this sphere into the bath. And now our sphere is going to have a temperature which depends on time because we have heat leaving our sphere. And this is going to be due to convection. All right, we know it's convection because we are given these H coefficients. Okay. All right, so if this quenching process begins at time t equals 0, then that means that the temperature of the salad is going to decrease as time increases. All right, so hopefully that is pretty intuitive. If you put a hot body into a cold fluid, eventually the fluid is going to cool it down until it reaches equilibrium, right? And so what we want to do is we want to find the temperature variation as a function of time. So we want to find this expression right here, where our temperature only depends on time, not on space. So because of that, we're going to use the lumped capacitance method to solve this problem. And we can do that because this method assumes that the temperature of the salad is spatially uniform at any instant during the transient process. And it also assumes that temperature gradients in the salad are negligible. So temperature gradients are like this. So what I mean by that is like the change in temperature versus X, the change in temperature versus Y, and the change in temperature versus Z. So because our temperature is constant in our body spatially, all of these derivatives would then be 0. Okay? Okay, so let's analyze this system. So our system here is just going to be the metal ball. It's, of course, a closed system. And we're going to make a few assumptions about this. So we are going to assume that the salad is incompressible. Which means that its specific volume is a constant. We're also going to assume that the temperature of the salad is lumped. All right, so that means that the temperature is only a function of time, not on space. And we're also going to assume that the fluid temperature is a constant. And it's equal to T infinity. All right, so what I'm saying by this is we're making an argument that the bath of fluid is large enough that the amount of heat it receives from the sphere is going to raise its temperature by a negligible amount. So bath is large enough that it experiences negligible temperature rise. Okay, so our system is the metal ball. We've made these assumptions, and then now we're going to look at our governing equation. All right, so we're going to look at conservation of energy for a closed system in rate form. We're choosing rate form because we need this DDT term because it's an unsteady process.
Ah,
Okay. All right, so what simplifications can we make for this equation? So we already know that there's no work happening to this steel sphere. I'm sorry, brass sphere. So we can get rid of our W dot terms. So there's no work. And we also know that the heat transfer is going from the hot object to the colder fluid surrounding it. So we have a Q dot out, but no Q dot in. And we also know that our Q dot out is Q dot of convection, right? That's the only mode of heat transfer that we have in this problem. And then I just wanted to also put in here to remind you that energy, so this DEDT term on the right is equal to this. So the total energy of our system is the mass of our system times internal energy plus its kinetic energy plus its potential energy. Now, we don't have any information in our problem that would suggest that we need to care about kinetic or potential energy. So I'm going to neglect both of these. So I'm neglecting changes in potential energy and changes in kinetic energy. All right, and so this equation with all of these simplifications becomes d dt of mu is equal to minus q dot of convection. Okay, so this is our simplified governing equation. Nothing new so far. The next governing equation that we have is our Newton's law of cooling. So this is our equation for heat transfer due to convection. All right, and so hopefully you've already noticed that we have q dot convection right here. And so we are going to use this equation on the right-hand side here. So I am going to substitute this definition into here, which gives us that the time rate of change of mass times internal energy is equal to minus h a t minus t infinity. All right. We're going to make use of one more governing equation here involving our specific heat. So this is from, I believe, topic 3 at the end. So this is from topic 3. We know that the change in internal energy is equal to the specific heat times the change in temperature. Okay, so just to remind you, C is equal to Cp, which is equal to Cv for a solid. All right, again, nothing new here. But we can use this expression in our governing equation here. But first, what I'm going to do is I am going to carry out this derivative on the left-hand side. And I guess carry out's a little too strong a word. I'm going to simplify this, right? So I have the time derivative of mass times internal energy. We know, of course, that internal energy is going to change as a function of time because we're losing heat to this object, but the mass of the object would remain the same, right? Conservation of mass. So that means that I can pull out the mass from this expression. And then my equation becomes mass times the time rate of change of internal energy is equal to minus h times A times the temperature difference. Okay. Yeah. Okay. So now what I am going to do is I am going to, now that my governing equation is in a form where I can make this substitution, I am going to substitute this expression for du into here. Okay, and so when I do that, I get m times c dt dt is equal to minus ha t minus t infinity. Okay. One other thing that I am going to make a note of is that we can rewrite the mass of our object using the density. So we know that mass is density times volume, or we could also write this as volume over specific volume. Okay. So I can rewrite this then as using this expression in here. I can write this as rho times volume, so density times volume, times my specific heat, change in temperature with respect to time is equal to minus HA T minus T infinity. Okay. Okay. So I am going to rearrange this a little bit, and I'm going to move everything over to the left-hand side and kind of write this in a more traditional way of writing an ODE. So I want to have my DDT term all by itself, and then I want to have a 0 on the right-hand side. So I'm going to divide through by rho VC. And then I'm going to bring the right-hand side to the left-hand side. All right, so when I do that, I get dt plus h times a over rho vc t minus t infinity is equal to 0. Okay, and so something that's interesting to kind of make note of right now is that this coefficient out front is a constant for whatever problem that we care about. Obviously, it'll change depending on the problem. So I'm going to call this constant coefficient B. So B is equal to H times A divided by rho VC. Okay. And that means I can write this expression as dt plus B T minus T theta is equal to 0. Okay, so this is just an ordinary differential equation. Which we'd like to solve. In order to kind of take care of some of the integration that we're going to do in a little simpler of a way, I'm going to make a substitution at this stage. So I'm going to let theta, which is a function of time because temperature is a function of time. So I'm going to let theta be T minus T infinity. Okay. So that means that I need to do something with dt. And I can write this in the following way. So I can just solve this equation for theta, or solve this equation that I have for theta for t and substitute it back in here. So I can say that t is equal to theta of t plus t infinity. Okay. And T infinity is a constant, so it is not going to change with respect to time. If you remember, we said that our temperature of our water bath or fluid bath, I guess I should say, is constant. So that means that this is just d theta dt. All right. Okay. So I'm going to put this all together, and I have finally that d theta dt plus b times theta is equal to 0. All right, so what I'm going to do then is I'm going to separate my variables and integrate. So when I separate variables, I want to have all the thetas on one side of this equation and then the t's for time on the other side. So I have d theta dt is equal to minus b theta. And then I'm going to divide both sides by theta and multiply by both sides by dt. So I have d theta over theta is equal to minus b dt. All right, the next thing I'm going to do is I'm going to integrate. So I have the integral of 1 over theta d theta is equal to the integral of minus b dt. All right, and when I do this, I get natural log of theta is equal to minus b times t plus some constant of integration. Okay? All right, so we want an expression for theta, so we need to solve this for theta. So I'm going to exponentiate both sides, so I have that theta as a function of time is equal to e to the minus bt plus c. All right, and then we know, of course, that this is the same thing as e raised to the c times e minus bt. And this is just another constant. So e to the c is just another constant. So I'm going to just call it c. And so I have finally that theta t is equal to c e minus to the minus bt. And we are always going to find c from the initial condition. Okay, so what I'm going to do next is I'm going to substitute back in my t minus t infinity for theta, which gives us the following. So subbing back in our definition that theta is equal to t of t minus t infinity, we get that t of t minus t infinity is equal to c e to the minus bt. Or we can write this as t of t is equal to c e to the minus bt plus t infinity. Okay, so let's solve for the initial condition. So we're going to find c by using the initial condition, which is t equals ti at t equals 0. Okay? All right, so we have that ti is equal to c e to the minus b times 0 plus t infinity. E to the 0 is just 1. And so we have that c is then equal to ti minus t infinity. So it's just the initial difference in temperature between our surroundings and the body. Okay, so that means that we can write down our full expression then. So the general expression is the following. So we have t is equal to ti minus t infinity times e, and I'm going to substitute in b as well here. So I have minus h a over rho cv times t. All right, so this is still b. All right, and then this is our key result for how the temperature in a body changes with respect to time if we can assume that the temperature in the body is constant everywhere spatially. Okay, so let's have a look at what this looks like. So if we look at our temperature with respect to time, we're always going to start off at Ti minus T infinity at T equals 0. And sorry, this axis is T of T minus T infinity. Okay. And we have an exponential with a negative value up there. So this is generally going to look like this. All right. And then as HA over rho CV increases, we'll find that this decays faster. So this is with an increasing value of HA over rho CV. Okay. Okay, so when that this term, so this is B, when this increases, then we find that the temperature changes more rapidly. And if you look at what this grouping of parameters is, that makes sense, right? So if your heat capacity is smaller or your volume is smaller, then B gets larger and means that that body is going to be more quick to change temperature. And then same thing as when H and A in the numerator increase, your body will be more likely to change temperature quickly as well. Okay, so let's go back to our original problem statement here. We wanted to find the temperature of that brass sphere after 1 minute. So we are going to start with our governing equation that we just derived. So we have T over T, or T minus T. Oh my gosh. T of T minus T infinity is equal to Ti minus T infinity times the exponential of minus HA over rho CV times T. Okay, so this is our equation that we just found. For a spherical ball, our surface area is defined as 4 pi r squared. All right, or in other words, this is pi d squared. And when I plug 2 centimeters in for d, this is 1.26 times 10 to the minus 3 square meters. And then we also need our volume. So our volume of a sphere is 4/3 pi r cubed, or if I plug in that 2 centimeters again, I get 4.19 times 10 to the minus 6 meters cubed. Okay, so outside of this, everything else has been given to us in the problem statement. So if we are immersing our sphere in water, we were given that the convective heat transfer coefficient is 250 watts per meter squared degree Celsius. So our HA over rho CV is then the following. So we have 250 watts per meter squared degree C times A, which is 1.26 times 10 to the minus 3 meters squared, divided by density. So that was given to us earlier in the problem statement, is 8522 kilograms per meter cubed times our heat capacity, I'm sorry, our specific heat, which is 0.385 kilojoules per kilogram degree C, and then times our volume. So we have 4.19 times 10 to the minus 6 meters cubed. All right, let's take care of our units really quick. So we have meters squared divided by meters squared. We have meters cubed divided by meters cubed, kilograms divided by kilograms, and then degrees divided by degree C divided by degree C, or degree C divided by degree C. And then what we have left is watts divided by kilojoules. But if you remember, a watt is a kilojoule per second divided by kilojoules. So this is units of 1 over S. So we get 0.023 per second. Okay, so I'm going to plug this in to our governing equation as follows. So we have T of T minus, I'm actually going to move T infinity over to the right-hand side. So I have T infinity plus Ti minus T infinity e to the minus HA over rho CV times T. All right, so if I plug in all the values that I was given, our ambient temperature is 50 degrees C, plus our initial temperature was 150 minus 50 degrees C, times the exponential of minus 0.023 per second times time. And the time that we want to calculate the temperature for is 1 second. So I'll put that in here. And so that means our temperature at T equals 1 second is 75.2 degrees C. Okay. I gave you way more space than you needed, it turns out. Okay, so the ball is also is immersed in air instead. So now our H is 50 watts per meter squared degrees C. So that means that HA over rho CV is now 4.58 times 10 to the minus 3 per second. And so then our temperature at a time of 1 second is equal to, again, T infinity plus Ti minus T infinity e to the minus HA over rho CV times T. And when I plug in all of those values, I have 50 degrees C plus 150 minus 50 degrees C times the exponential of minus 4.58 times 10 to the minus 3 per second times 1 second. And I get 126 degrees C. Okay. Okay. And actually, I'm going to use this space right above here to make a comment. So we noted this before, but HA over rho CV, so this constant out front, has units of 1 over time. All right, so that means that we can use this to define a thermal time constant. And we're going to call this time constant tau. And tau is just 1 over our constant that we originally had. So we can have tau is equal to rho CV over HA, and now that has units of seconds. And I can combine M and V into mass, so we can also call this specific heat times mass divided by H over A. Okay? So I can use this concept of tau to rewrite our solution then as the temperature minus our ambient temperature is equal to Ti minus T infinity times E minus T over tau. Okay? So if you think about it, what does tau represent? So if you look at what the temperature is at T equals tau, we have the following. So we have T at T equals tau minus T infinity equals Ti minus T infinity times E to the minus tau over tau. All right, so we have Ti minus T infinity times E to the minus 1, which is 0.3678 Ti minus T infinity. So what this means is that the temperature difference T minus T infinity has dropped by 63.22% relative to the initial temperature difference. Okay, and then by a similar argument, which I'm going to write over here, at T equals 5 tau, the temperature difference has dropped by 99.3%. Okay? Okay. One last comment because this will be useful to you on homework. So if you wanted to find the time it takes for an object to reach a specified temperature, and I'm going to call this T naught, then we're just going to solve this expression for the time. Okay, so if we have T naught minus T infinity is equal to Ti minus T infinity e to the minus T over tau. What I'm going to do is I'm going to divide both sides by Ti minus T infinity. So I have T naught minus T infinity divided by Ti minus T infinity is equal to the exponential of minus T over tau. Now I'm going to take the natural log of both sides. So I have natural log of T naught minus T infinity over Ti minus T infinity is equal to minus T over tau. All right, and now we have our expression for T. So where am I going to put this? So I have T is equal to minus tau natural log of T naught minus T infinity divided by Ti minus T infinity. Okay, so that's just the same equation that we've been using, and I've just solved it for time. All right. Okay, so the last little bit about this is talking about the validity of this lumped capacitance method. So this equation that we derived, so this transient solution we found, is very simple, and it's also very useful. But if you remember, we made some assumptions when we derived this equation. And that was that we assumed the temperature of the solid was spatially constant, right? Or spatially uniform. All right. So the question is, how do we know when this assumption is okay to make? Okay. So we would like to develop some type of a criterion in order to evaluate quantitatively whether or not we can make this lumped capacitance assumption. Okay, so to do this, we're going to consider steady conduction through a wall. So just a regular wall of area A, thermal conductivity K, and a thickness L. One surface is maintained at a temperature, and then the other surface is exposed to the fluid temperature. And we're going to let T2 be the temperature of the surface exposed to the ambient fluid. So I'm going to just draw a picture here. So here's our infinite wall. On this side, we have our constant maintained temperature T1. And then over here, we have T2 on the other side of our wall. And we have exposed on this right-hand side of the wall is some ambient fluid with a convective heat transfer coefficient H and an ambient temperature T infinity. We're going to call this the X direction. And then we have a width L. Okay, so under steady conditions, we can write our rate of heat transfer from convection as in the following way. So we know that the heat transfer due to conduction has to be equal to the rate of heat transfer due to convection. All right, so I'm essentially equating the conduction heat transfer and the convection heat transfer at this surface where they're making contact. Okay. Okay, so we can rewrite this with all of the temperatures on the left-hand side. So I'm going to say I have T1 minus T2 divided by T2 minus T infinity. And then I'm going to move all of those other material properties and our convection, our coefficient of convection all on the right-hand side. So I have HA over KA times L. All right, which of course simplifies to HL over K because we have A divided by A. And it turns out that this is a special number. So this is what's known as the BO number. All right, and this BO number is going to give us a measure of the temperature drop in the solid compared to the temperature difference between the surface of the solid, between the solid surface and the fluid. Okay, so if our BO number is less than 1, and I guess I should write this. So BO number is given the symbol Bi. So Bi is HL over K. The resistance to conduction within the solid is much less than the resistance due to convection across the boundary layer. And we can reasonably assume a uniform temperature distribution. Okay, so this is good. This is very useful. So we have a criterion that we can make use of. But we need to talk about this a little bit more because you'll notice that we have our convective heat transfer coefficient. That's fine. We've already generally have that for any type of problem. And then we also have K, which we have if we know the material of our object, but we have this L here. So L was the width of our wall, which is fine. But if we are considering an arbitrarily shaped solid, we need to find a characteristic length scale to use that's not just L, right? So like L doesn't necessarily mean anything in our example where we had the sphere. Okay, so let's just talk about that a tiny bit. So what we're going to do is the following. So for our sphere, or any arbitrarily shaped solid, we're going to use our characteristic length that's equal to the volume of that object divided by the surface area. All right, so this is volume of the solid. And then A is the heat transfer area for convection. So essentially, this is the area exposed to the fluid. Okay. Okay, so for practical problems, before I said if the BO number is much less than 1, then we can use this lumped capacitance method. That's still a little ambiguous. So practically speaking, if BO number is less than 0.1, we can assume that the temperature of the solid is uniform and only depends on time. So we can use lumped capacitance. Okay, so let's go back to our 2 centimeter sphere because we did that problem assuming that lumped capacitance was fine. So let's just check if it actually was a good assumption. And we will do that by calculating the BO number. All right, so first we want to calculate our characteristic length. So we have volume divided by area, which was 4 pi r cubed over 3 times 4 pi r squared, which simplifies to r over 3, which was 0.333 centimeters. All right, so when we had our immersed in water case, our BO number is HLC over K. So we have 250 watts per meter degrees C times 0.33 times 10 to the minus 2 meters divided by 111 watts per meter degrees C, which gives us 0.075, which is, of course, less than 0.1, so we are good. For our immersed in air case, we have a similar expression to work out, but now our H changes. So we have 50 watts per meter degree C times 0.333 times 10 to the minus 2 meters, oops, divided by 111 watts per meter degree C. And so we get 0.0015, which is still less than 1. And so this one is okay too. Okay, so for both of these cases, the lumped approach was valid. So that's good. And then one last note here. So if you have a solid with a surface coating that provides extra thermal resistance, we can use the overall heat transfer coefficient U in the definition of the BO number. So this would be given to you in a problem where that is the case. So if you have sort of this coated substance, then you would be given this overall heat transfer coefficient U.